This presentation will cover some of the research performed here at Mississippi State University. This particular study is titled The Evaluation of Dicamba Drift in Soybean when Applied Under Field Conditions. New technologies, like the upcoming 2,4-D and dicamba-tolerant cropping systems, could potentially provide many benefits for producers. These benefits could come in the form of more and alternative weed control options. They could also help a producer deal with managing resistant weed species populations by providing alternative modes of action. However, with these benefits also comes the increased concerns for issues such as herbicide drift, volatility, as well as tank contamination. Now, the EPA defines pesticide drift as the physical movement of pesticide droplets or particles through the air from the target site. Past research has identified several key factors of herbicide drift. The first of these would be the size of the spray droplet produced. Now, droplets are found to be subject to drift if they have a diameter of 100 to 200 micrometers. Another key factor of herbicide drift would be the height at which the application is made. This is particularly a problem in aerial applications. One previous study found the potential for herbicide drift up to 198 meters increased as the spray height increased, while the highest spray release height in this study of 9.1 meters had the greatest potential for drift beyond this distance. And the final factor of herbicide drift would be the environmental conditions under which the application is made. So things like wind speed and wind directions should be taken into account, as well as the potential for a temperature inversion. Because of these risks, research is being conducted to determine different management options that may minimize physical spray drift. Our current research looks at different nozzle types as well as new herbicide formulation and nozzle combinations. Our objectives of this particular study, we wanted to quantify the effect of dicamba drift on non-dicamba tolerant soybeans when applied through a commercial applicator. And we also wanted to estimate the distances to no plant effects from these large-scale spray applications for various locations. The herbicide treatment used in this study was the experimental compound M1750. Now, this is an experimental formulation of a pound of glyphosate and a half pound of dicamba per acre. We applied this at a rate of 48 fluid ounces per acre. We also included as a pH stabilizer dipotassium phosphate at 2% volume for volume, as well as interlock drift retardant at 4 fluid ounces per acre. This experiment was conducted at several different locations, all of which use some form of Roundup Ready soybean variety. Here you can see the planting date for this study for all the locations. Planting dates ranged anywhere from the beginning of May to the end of June. Our row spacings used in this study were soybeans planted on either 30 or 38-inch rows. Here you can see the application dates for each location. And then here's our soybean growth stage at application. Our target growth stage for this test was the R1 to R2 soybean growth stage. There was one location, our Arkansas locations, in which the application was delayed till the soybeans had reached the R4 growth stage. This is going to be important whenever we start looking at our results. All treatments were applied with TTI spray tips. Delivery volume was 15 gallons per acre. There was one location that used a carrier volume of 12 gallons per acre. Here you can see our ground speeds for the treatment. Our ground speed ranged anywhere from 5.8 miles per hour all the way up to 9.3 miles per hour. Our boom height was set at 20 inches above the crop canopy. Boom widths ranged from 40 to 90 feet, with the majority of our booms being 60 feet wide. Plot lengths, our treated area length was 600 feet long. There was one location that used a 550-foot treated area. Here you can see the wind speed maximums and minimums for each location. And then finally here are our wind speed averages for each location. Average wind speeds ranged anywhere from a low of 4.6 miles per hour all the way up to 8.5 miles per hour. Our target wind speeds for this study were 5 to 10 miles per hour winds. This slide shows our experimental layout for this study. As you can see in the middle of our picture there in the treated area in the tan box, the soybean rows were planted parallel to the treated area, so running from the left to the right. Our wind was moving from the top of the screen here to the bottom. So what we would do, we mixed our tank up, we mixed our sprayer up, we took it to a location away from our test area, and we primed our boom. And then we pulled up to the beginning edge on the left side of the treated area, and then we sat and waited till our wind speed and our wind direction got to where we wanted it to be, and then we made our application to allow the herbicide particles to drift onto the downwind portion of the field. Now, our rating transects are designated in the blue by the blue boxes, set up 150 feet apart throughout the treated area. The spacing between the blue boxes represents the intensity with which we took our ratings. At distances closest to the treated area, we took ratings in every 4-row skips. Out past that, we started taking ratings in 8-row skips, and then we started taking ratings in 20-row skips on out to our furthest distance away from the treated area. Now, the green boxes on the upwind side of the field, as well as the downwind portion on the left and the right side of your screen, were where we set up our check plots for comparison. As far as the actual data that we collected, we had a weather station on site to collect data during and after the application. During the application, it was set to record every 1 second. For the following 48 hours, we switched it over to where it recorded data every 1 minute. Our observations were made on the center 2 rows of each experimental unit. We took percent visual injury and plant height data at 14 and 28 days after treatment, and then we also recorded on these same areas yield to assess any potential herbicide drift effects. This graph shows our 1 second wind speeds during our application at our Brooksville, Mississippi location. The x-axis is our application time in seconds. The left axis would be our application or our wind speed in kilometers per hour, and our right y-axis would be our wind speed in miles per hour. You can see that we had some low wind speeds and some particularly high wind speeds. But for overall, our dotted red line there is our average wind speed for that location, and overall we were well within our target wind speed range. I'd like to talk to you a minute about the statistical methods that we used to analyze this data. For our plant height and our yield data, we used a segmented regression analysis model, which fits one line with an upward sloping positive trend, which suggests some sort of herbicide effect at close distances, which would rise to a second horizontal line, which would suggest no herbicide effects. Now, the meeting point between these two lines, or our hinge point, estimates the distance to no dicamba effect. I mentioned we use this for plant height and our yield data, and for our injury data, we used a linear regression of malformation with a log of the distance, in which we fit a log linear relationship between percent visual injury and distance, and then identify the distance for which injury dropped below 5%. This slide shows a picture of our test area in Brooksville, Mississippi. The left-hand side of the screen would be the downwind side. The top edge here is where our treatment application began, and you can see here along the edge the drift plume, the soybeans curling up, the soybean response to that dicamba herbicide. Pretty evident here in this picture where the dicamba hit and where it didn't. This is the same field from overhead. Again, the downwind portion is now on your right side of the field. You can kind of see the drift plume in this. If we zoom in and play with our color a little bit, it becomes much more evident. You can see there on the right side of the field where that dicamba hit. These pictures show the injury that we were seeing on the ground. This first picture is the furthest distance away from a treated area that we took data. Soybean injury here was 0%. Here at 295 feet away from the treated area edge, we saw visual injury of about 5%. You can see in this picture some of the soybean leaves there cupping up, and some typical dicamba symptomology there on our soybeans. Here we have about 20% visual injury, and this is 175 feet away from the treated area edge. Soybean plants are somewhat stunted compared to those that did not receive any soybean injury. And then again, you see some of the twisted stems, the epinastic responses there, and still the cup leaves are a little more severe in this picture. And here we have, at about 15 feet away from the treat area edge, soybean injury of about 50%. Here the plants are severely stunted and twisted and cupped. Visual injury is pretty evident in this picture, but I also want to point out the difference in canopy closure that we see at these different distances. So not only are you talking about the potential for direct yield losses due to soybean injury from drift, but also some potential for weed species to pop up and compete with your soybeans there for nutrients and then cause you some yield losses there as well. This slide shows the visual injury results from our Brooksville, Mississippi location. The x-axis on both of these graphs is the distance from the treated area expressed in feet. The y-axis on both of these graphs is percent soybean visual injury. The top graph reflects data collected at 14 days after treatment, and the bottom graph reflects data collected 28 days after treatment. Now the blue points you're seeing on the graph here reflect the actual visual injury seen at each distance from each location for all the transects. Here you can see the visual injury ratings averaged over all 5 transects at each distance. And here you can see our regression line for percent visual injury. The bold dark red line there, curve, is our regression. The left vertical bar on each of the graphs represents the distance beyond which percent visual injury dropped below 15%. This was 142 feet 14 days after treatment and 135 feet at 28 days after treatment. Now, the right vertical bar on each of the graphs represents the distance beyond which soybean injury dropped below 5%. This was 295 feet at 14 days after treatment. At 28 days after treatment, this had dropped down to 257 feet. This slide shows the results For the visual injury from all the locations, before I get talking about numbers, I'd like to point out this one location here, the Norsworthy location, where we had all these zeros where no dicamba effects were found. If you'll remember back, this was the location where the treatment application got delayed until the soybeans had reached the R4 growth stage, based on prior research done here at Mississippi State University, which looked at several different rates of dicamba applied to soybeans at several different growth stages. We found that the R3, R4 growth stage is typically when dicamba responses in soybeans were not seen anymore, and that's why we didn't see any injury at this location because of that delayed application. As far as the other locations go, our distances beyond which visual injury dropped below 15% at 14 days after treatment ranged anywhere from 37 to 142 feet away from the treated area edge. At 28 days after treatment, these distances were anywhere from 49 out to 135 feet from the treated area edge. The distance beyond which a percent injury dropped below 5% at 14 days after treatment ranged anywhere from 72 feet from the treated area edge out to 295 feet from the treated area edge. At 28 days after treatment, these distances had changed from 83 feet all the way out to 257 feet from the treated area edge. Moving on to our plant height analysis, the top graph on this slide reflects our data collected at 14 days after treatment, while the bottom graph reflects our data collected after 28 days after treatment. The x-axis on both of these graphs is our distance away from our treated area edge expressed in feet. The y-axis on both of the graphs is plant height in centimeters. The blue points on each of the graphs indicates the plant height measured at each rating transect and at each distance away from the treated area edge. Here you can see the average plant height at each rating distance. And here now you can see our segmented regression analysis. As I mentioned earlier, the upward sloping line there indicates distances at which dicamba effects were seen. The second line that it joins, the horizontal line with zero slope, reflects distances at which dicamba effects were not seen. Again, the hinge point, the meeting point between the two lines, estimates our distance to no effects on plant height, no dicamba effects on plant heights at 14 days after treatment. This distance was just over 50 feet away from the treated area edge. At 28 days after treatment, this was about 60 to 70 feet away from the treated area edge. Moving on to our yield reduction analysis, again, we did a segmented regression analysis on this, as the same as plant heights. Our distance there on our x-axis is feet from the treated area edge. Our yield on the y-axis is in bushels per acre. Our blue points, again, on the graph represent yield collection at each distance and each rating transect. Here are our average yields from each distance. And then here's our regression analysis. Our distance to no dicamba effect on soybean yields at this virtual location was 63 feet. This slide shows our result summary table from our segmented regression analysis of our plant height and yield data. Again, I'd like to point out the Norsworthy location at which plateaus were not detectable. Again, we attribute this to the growth stage at which the applications were made. At 14 days after treatment, the distances to no effects in plant height were seen anywhere from 21 to 84 feet away from the treated area edge. At 28 days after treatment, distances to no effects in plant heights were seen anywhere from 23 to 69 feet from the treated area edge. And getting onto our yield data, distances to no dicamba effects on our soybean yields were not detectable at the Barber and Childs location, as well as the Norsworthy location. At locations where dicamba effects on yields were seen, these distances to no dicamba effects were found anywhere from 14 to 63 feet away from the treated area edge. In conclusion, distance to reduction in plant heights were typically found to be less than those observed for 15 and 5% visual injury at both 14 and 28 days after treatment. Also, distances to yield reductions were either non-detectable or numerically less than those observed for 15% visual injury at 28 days after treatment. In the future, we'd like to continue to perform these large-scale experiments to determine herbicide drift effects. We intend to use determinate versus indeterminate varieties, as well as different soybean maturity groups.